So we're talking about vertex-edge graphs, so it'll be useful to know what a vertex is and what an edge is. So here's a vertex. It's like a point. You can also think about it as a corner. If you pick up a box, each corner could be a vertex, and you could make a graph of it, but I'm getting ahead of myself. If you have more than one, they're called vertices. Don't say vertexes, it's vertices. And if we have a connection between two vertices, that is an edge. So we could say that we have vertex A, vertex B, and we call this edge 1. So with this, it's pretty easy to just keep track of visually. Eventually you might want to start making a list of your vertices and your edges. So that list might look like A, B for your vertices, and 1 for your edges. Now you could also make a note off to the side that 1 is an edge that goes from A to B. Now you might wonder why I didn't just use AB as the name of edge 1. The answer is you can have more than one edge between the same two vertices. So you have edge 2 that also connects A to B. Now you could also have an edge that connects a vertex back to itself. That's called a loop. You can see why it's called a loop. It's named for how it looks. So now we have edges 1, 2, and 3, where 3 we could call BB as far as in terms of what it connects to what. Okay, so we could have another vertex that we call C, and we could have an edge that goes from A to C. And that's all the vertices and edges that I'm going to set up here because I'm running out of room, but you can keep going if you want to. Now this is something that we can do just to doodle. It's also something where you might want to start investigating things about it. So then it becomes useful to have certain ways of talking about it. So if you want to talk about the degree of the vertex, that's how many edges connect to it. So sometimes that's written using the absolute value symbols. There are other notations also. Just anytime you're reading a book on graph theory, make sure you read the first chapter just to find out what the notations are if you don't need it for any other reason. So we could say that the degree of vertex C is 1 because it has one edge connected to it. So the degree of vertex A would be 3. You can count that up easily. Now, where this gets a little bit twitchy is you need to keep track of both ends when you have a loop. So the degree of vertex B would be 1, 2, 3, 4, because it really counts the ends. So you notice that you can have odd degree vertices or even degree. Let's see. You can also have graphs that are more or less thoroughly connected. Now here's what I mean by that. Starting back with an extremely simple graph, obviously nothing's connected here, and then here you have every possible pair of vertices being connected. So that's an interesting version of a 2-vertex graph. Now we can set another graph that has 3 vertices A, B, and C, and we can say, okay, we want A to connect to B, and A to connect to C. Well, then B already connects to A, but then we want B to connect to C, and C already connects to both A and B. So now again, we have a completely connected graph here. Now with 4 points, the first way you most naturally think to set it up would be in a box shape. And so you'd say, okay, A needs to connect to B, A needs to connect to C, and A needs to connect to D. Well, then B is connected to A, but it needs to connect to C and D. Now we've got an intersection in the middle. We specifically do not draw a point there, and if some of our vertices are looking a little small in relation to the size of the edges, we might go back and make them bigger, just to make it easy to tell that we're specifically not saying that there's a vertex at that crossing. They are allowed to cross. A graph that you can draw without any crossings is called planar because it works well on a 2D surface. Graphs that can't be drawn on a piece of paper without these kinds of intersections are called non-planar, and one thing we try to do with graphs is try to find a way to draw them planarly, but I'm getting ahead of myself again. So C is connected to A and it's connected to B, but it needs to connect to D, and there we have it. So one thing you can do with this is investigate... my apologies for that. Okay, where were we? So we've got a 4-point graph here, and we've got all its vertices connected with one edge to each other vertex. So right now it's not drawn in a planar way, but as it turns out, there's a way we can make a slight adjustment to this graph to make it planar anyway, and that would be to take this vertex and move where we're drawing it to about there. So what we have here is vertices A, B, C, and D, and now we just need to draw back in the edges to see what this will look like this way. So A connects to B, and to C, and to D. B connects to C, and to D, it's already connected to A. C connects to D, it's already connected to A and B, and D is already connected to A, B, and C. So you see, by scooting that one vertex in, we were able to come up with a planar drawing of this graph that has edges between each pair of vertices. We can also look for some interesting number patterns in here. So we can take the numbers of edges and vertices and see what we have here. So when we had 2 vertices, we had 1 edge. When we had 3 vertices, we had 3 edges. So in one graph you have fewer edges than vertices, in another you have the same number, and then in this third graph that has 4 vertices, let's see, 1, 2, 3, 4, 5, 6, we have 6 edges. Now, you can investigate further, sketch out more points, see how many edges you come up with, look for number patterns in the number of edges that go with the number of vertices, and all sorts of things like that. And you can look for some interesting things this way while doodling. Now here we have a graph that represents the vertices and edges of a 3D box. And you would have a lot of excuse for thinking that this cannot possibly be planar, right? But if we make a couple of adjustments, so let's see, what adjustments could we make? Well, I see that we could push this vertex in there, and that one in there, and that one in there. So let's see, we would still have this vertex here, and that one there, and that one there. Now this one would be in here. This one would be in there. This one still is where it is. Let's see, this one is still here, but this one is in there. And so if you look then at the connections between these vertices, so at what edges we need, we've come up with a completely planar representation of a 3D object. And now if you think about nets of a box, this actually isn't that surprising, because what we're looking at here is as if we had the net only with that and that together, and so on. So that this edge and this edge are actually the same edge, like they would be when you fold it back up together. So one thing we talk about with 3D boxes is the number of faces, the number of surfaces. So as we know already from having worked with cubes a bunch of times, it's got a face here at the bottom, and then here, 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 and here around the sides, and then here at the top. So 6 faces. Now when you look at a graph like this, you see different regions. You've got the middle, so that's 1. And then 2, 3, 4, 5 around the regions that are bounded. Now you also have this unbounded region up here. And the way you need to think about that is that's like the top of the box. Like if you left box open, that's where you would need the lid. So to represent that number-wise for convenient counting purposes, we say that the outside of the graph represents a face also, and so we still have 6 faces. Now there are other things you can do with these numbers. You can look for patterns just the way we did with the other one. You can look at what kinds of 3D objects can be broken down this way. You can do all kinds of investigations while doodling with vertex-edge graphs. And I'd like to see some of the investigations that you all come up with in the comments section.